Howdy folks, this discussion is going to be all about Dirac Delta Functions. They appear in all different areas of STEM. In my background in physics, I saw them quite a bit in E&M and in quantum physics. If you're doing any amount of signal processing, they show up quite a bit there as well. I know that because I'm doing higher energy astronomy and astrophysics and a lot of signal processing. I've been working with these a lot recently, hence why I'm doing a discussion on them. And so that's why we're talking about it. So without further ado, let's dive right in. Now, I want to forewarn you that Dirac Delta Functions are not necessarily the most intuitive from the beginning. So I'm going to define the Dirac Delta Function for you right here. This is a Dirac Delta Function centered at 0. You can move it around, center it at like plus a or minus a. But we're just going to deal with like the simplest Dirac Delta Function right here, centered at 0. And the Dirac Delta Function is defined such that the Dirac Delta Function is 0 for everywhere that the Dirac Delta Function is not centered. So in this case, for anywhere that's not 0, the Dirac Delta Function is 0. But at 0, the Dirac Delta Function is infinity. Or wherever the Dirac Delta Function happens to be centered at is infinity. Now, conceptually, that seems a little bit weird, to me at least, the first time that I heard it. It might sound weird to you if this is the first time you're hearing it. But what really makes the Dirac Delta Function really useful is when we integrate it. So if we integrate the Dirac Delta Function over all space, sorry, that's just natural for me with a background in physics. Anytime I see x, I say space. Anyways, if we integrate the Dirac Delta Function from negative infinity to infinity, that whole thing is going to be equal to 1. So that's like the most useful property of a Dirac Delta Function, is integrating it, because this should be ringing alarm bells for you if you're, have any experience with quantizing things or statistics. Whenever you take the integral of something and the sum of it is 1, that should scream probability to you, or like quantization or something like that. And so that's what makes this Dirac Delta Function so useful. But even more so than that, another property called the Sifting Property is what makes it so useful. If we have some function f of x multiplied by a Dirac Delta Function centered at some value a, and we integrate that, that's just going to give us our function evaluated at wherever the Dirac Delta Function is centered at. So f of a in this case. Now that's just a basic definition of the Dirac Delta Function and just one of the really useful properties, which is the Sifting Property. Let's go and look at some examples. So the first example that we're going to look at right here is really simple. We're just going to be evaluating x squared, okay, times the Dirac Delta Function centered at 2, and we're going to integrate that over negative infinity to infinity, okay? That's just going to be x squared evaluated at x equals 2, since that's where the Dirac Delta Function is centered. Everywhere else, everything else under the curve is 0, so it's just going to be x squared evaluated at x equals 2, which is just 4. It's pretty simple and pretty straightforward, right? But now let's change this ever so slightly, all right? We're going to change our bounds of this to negative 1 to 1. You might think, well, it's the same thing. You just changed the bounds. We're going to evaluate this x squared at x equals 2. It's still going to be 4. That's not correct. Our bounds are negative 1 to 1, and our Dirac Delta Function is centered at positive 2. So that falls outside of our bounds. And what do we know about the Dirac Delta Function? Well, the Dirac Delta Function is 0 everywhere it is not centered at. So the sum under the curve between negative 1 and 1 is 0. This whole integral is 0. And that makes things really nice and really easy, right? If we wanted to be able to evaluate this, we just had to make sure that our Dirac Delta Function is centered within the domain of the bounds of our integration. So you could do like 0 to 5, and it would work out perfectly fine, and the solution would still be 4. You'd still just be x squared evaluated at x equals 2. And so that's something really important to pay attention to, is not everything is negative infinity to infinity. If you have finite bounds, you got to kind of make sure that the Dirac Delta Function is centered within the bounds of your integration. But those are just some basic properties and kind of like the most important properties of Dirac Delta Functions. There's some more things that we can say about Dirac Delta Functions, some additional properties. The first thing is that the Dirac Delta Function is, after all, a function, and it's an even function, meaning that delta x is equal to delta minus x. We can also scale Dirac delta functions. If we have a delta function with c of x, that's just equivalent to 1 divided by the magnitude of c, or absolute value of c, times delta x. And the other thing, too, that might be a little bit confusing to you is that you can take derivatives of Dirac delta functions. So if we take a similar looking thing to that sifting property, so we're going to integrate from negative infinity to infinity. We have some function f of x, and this time we have the derivative of a Dirac delta function centered at some real value a. That's just going to be minus f prime of a, okay? Or minus f prime evaluated at a, all right? I'm not going to do a whole proof of any of this stuff. If you want to see that, leave me a comment and maybe I could do that later on. Okay, so with that, let's jump into 2 more examples. We'll do one for scaling and another one for the derivative property. Okay, so kicking things off here, we have another very similar looking integral just like before. We've got the integral. Our bounds are negative infinity to infinity. We're not going to go back and mess with the bounds again. I already made my point with one of the previous examples. But we've got x squared times the delta function 2x minus 8. Okay, so this thing is clearly being scaled right here. And so we can evaluate this using what we just learned. So what we're going to get is 1 on the absolute value of 2 times the integral, negative infinity to infinity, of x squared times our delta function centered at positive 4. And so that's pretty simply just x squared evaluated at positive 4. So it's 16 divided by 2. So our solution is 8. Now let's do one with a derivative. In this case, we've got the integral, again, negative infinity to infinity, of cosine x times delta prime centered at negative pi. And so this integral is just going to be minus the derivative of cosine of x evaluated at x equals minus pi. So derivative of cosine is minus sine, double negative. This is just sine. Sine evaluated at positive or negative pi, though, is just 0, so this whole integral is 0. Congratulations. Now here's the thing, though. If we combine both of these properties, the scaling and the derivatives, we can generalize this for multiple derivatives, because you could take more than one derivative of a delta function. I've personally never encountered a reason to do that, like in real-world applications in physics or signal processing or whatever, but it is possible. You could do it. And in that case, this is what the delta function looks like. You're going to get, for n derivatives, okay, and your scaling factor c, this is what this whole thing looks like. It's going to be negative 1 to the n divided by the magnitude of your scaling factor raised to the n plus 1 power times, n derivatives of your delta function, and this one's just centered at 0. So let's do one final example here where we put this all together. We've got the integral, bounds are negative infinity to infinity again, and this is going to be an integral of sine of x times delta prime 2x minus 2 pi dx, of course. So that's going to give us negative 1 on 2 squared, so that's just negative 1/4 times first derivative of sine, and all that's going to be evaluated at x equals pi. Well, the derivative of sine is just cosine, so we get negative 1/4 times cosine evaluated at x equals pi. So that's just going to be positive 1/4 because the cosine of pi is negative 1. And again, I would strongly encourage any of you that to get extra practice, just come up with some practice problems. Ask an AI if you want. Just do about a half dozen of these, just like we did right here. We did 6 examples. Just do at least a half dozen of these, and you're going to get a lot better at doing these things. But anyways, that was the Dirac Delta Function, at least the basics of the Dirac Delta Function and the sifting property. Again, when you see these things, you should be thinking about point sources, or at least evaluating some kind of integral. Anyways, thank you all very much for watching. If you got questions, comments, or concerns, don't hesitate to let me know. If you find any mistakes, I'm not perfect, okay? So let me know in the comment section. But otherwise, thank you all very much for watching, and I hope to see you all again next time.